In this segment, we'll talk about how to calculate coefficients of moisture expansion through an example. So we'll be calculating both the longitudinal coefficient of moisture expansion of a unidirectional lamina as well as the transverse coefficient of moisture expansion in the lamina, also denoted by beta 1 and beta 2 respectively. Let's go and review the formulas, general formulas for the coefficient of moisture expansion. This is the formula for beta 1, this is the formula for beta 2. And the reason why I am showing you these formulas is because I want to iterate the fact that the moisture expansion coefficients are not just dependent on the volume fraction and the moisture expansion coefficients of the fiber in the matrix, but also on the Young's modulus of the fiber in the matrix, and also the density of the composite and the longitudinal modulus of the composite, but also how much of it is taken, how much of the moisture concentration is in the fiber and how much of the moisture concentration is in the matrix, which can be different for the fiber and the matrix. So it's unlike thermal expansion coefficients where we assume that the temperature change is same in the fiber and the matrix. You're also finding out that in order to calculate beta 2, for example, we need an additional parameter which is called nu1,2, the major Poisson's ratio. As we saw in the theory that these formulas do become a little bit easier, or I should say simpler, if your fiber is not absorbing or deabsorbing moisture. So you could have fibers such as graphite, for example, and we can consider to be not absorbing or deabsorbing moisture. Then the formulas for beta 1 and beta 2 become a little bit simpler. And you also find out that it becomes independent of the concentration of the moisture in the matrix itself, which makes it a little bit simpler to use because now it is just based on the material properties as opposed to how much of the moisture is in the fiber and how much moisture is in the matrix, which can make it difficult to calculate the values of beta 1 and beta 2 otherwise. So the example which we're taking is of a composite lamina where the fiber is not absorbing or deabsorbing moisture. So here is the example here. We have to find beta 1 and beta 2 of this glass epoxy unidirectional lamina, which has 70% fiber volume fraction. The properties of the fiber and the matrix are given below, which is the Young's modulus of the fiber, the Poisson's ratio of the fiber, the moisture expansion coefficient of the fiber, and the density of the fiber. And same properties are also given for the matrix. So we have to somehow find out beta 1, beta 2. It's also given that you can assume that the glass does not absorb moisture. So we are going to, of course, assume delta CF is equal to 0. So if we are looking at the volume fraction, which is 0.7, because 70%, the volume fraction of the matrix will be 1 minus 0.7, which will be 0.3. So keeping these two things in mind and making and establishing that the fiber is not absorbing or deabsorbing moisture, let's go and calculate beta 1 and beta 2. So we have beta 1, which is EM divided by E1, rho C divided by rho M times beta M. So before we start any kind of substitution in this formula, we have to calculate the density of the composite and the longitudinal Young's modulus of the composite, the unidirectional lamina. So let's go and calculate E1, which is given by this formula right here. And we know that these properties are given as Young's modulus of fiber is 85, volume fraction is 0.7, Young's modulus of matrix is 3.4, volume fraction is 0.3, and that gives us 60.52 gigapascals. Of course, we need rho C also, which is the density of the composite, again given by a rule of mixtures formula. The density of the fiber is given to us as 2500 kilograms per meter cube. We know the volume fraction of the fiber. Density of the matrix is given as 1200 kilograms per meter cube. We know the volume fraction of the matrix. And this gives us a density of the composite to be 2110 kilograms per meter cube. So now what we're going to do is we're going to use these values E1 and rho C in this formula to be able to get what the value of beta 1 is. Let's go and calculate beta 1. Beta 1 is EM divided by E1 rho C divided by rho M times beta M. So EM is 3.4, E1 is 60.52. If we convert it into pascals, we can just multiply by 10 to the power 9, both the numerator and denominator, which will cancel out. Rho C is 2110, and this one is 1200. Beta M is given as 0.33. So if we take this, the value which we get is 0.03260. And what are the units of moisture expansion coefficient? They are meter per meter per kilogram per kilogram. So in order to calculate beta 2, we write the formula again, which is this. We have already calculated the density of the composite. We already calculated beta 1, which is the longitudinal moisture expansion coefficient. But we do need to calculate nu1 2. So nu1 2 is given by this formula right here, rule of mixtures formula. So we calculate nu1 2. This is 0.2. This is 0.7. This is 0.3, and this one is 0.3 as well. So we get 0.23 as nu1 2. So let's go and calculate beta 2 now. It's 1 plus the Poisson's ratio of the matrix, which is 0.3, times rho C, which we calculated in the previous slide to be 2110 kilograms per meter cube. The density of the matrix is 1200. The moisture expansion coefficient of matrix is 0.33. Beta 1 we calculated previously as 0.03260, and then we had the major Poisson's ratio just calculated with 0.23, and this number here turns out to be 0.7468 meters per meter per kilogram right here. Those are the units of beta 2. And that's the end of this segment.